Okay, so now we are starting the talk. Thank you very much for your patience. So this is we're going to cover advanced topics. The advanced topics to do with OpenMP offload. So we're going to cover a number of areas. We're going to talk about OpenMP offload interoperability with ROCm and HIP. ROCm is just a suite of software provided by AMD to help you program their GPUs. So it will provide things like compilers, debuggers, and profilers, as well as libraries that will allow you to do things like fast Fourier transforms or various linear algebra operations. Then there's HIP, which is their programming model, which allows you to directly interact with a GPU, such as allows you to allocate memory on the GPU, transfer data, and also to invoke a kernel. We use the term kernel here to indicate a piece of computation that's to be executed on the GPU. NVIDIA have their own equivalents of this, so their equivalent of ROCm is the HPC SDK, and their equivalent of HIP is, of course, CUDA. NVIDIA support for GPU has been around for quite a bit longer than AMD, so you'll find that the AMD HIP is very similar to CUDA. Main intention of that is obviously to allow programmers who are used to CUDA easily transfer over to AMD GPUs. We'll also then talk about custom data mappers. So you've seen with the OpenMP offload examples that you've done, you would have mapped base types, an array of integers or doubles. So we're going to look at doing the same thing, but with more complex heterogeneous types. We'll then look at the types of memory that are in play when you're programming for GPU. And then we'll look at the various ways in which you can control the allocation, which type of memory you are allocating, how that memory is allocated, and then restrictions as regards memory access. And then finally, we'll cover asynchronous tasks. And that's to do with the basic OpenMP offload operations, such as data sharing and invoking kernels. Those things are by default blocking, but we'll show how to run those asynchronously. So first, I'll talk about OpenMP and ROCm compatibility. So you may be in a situation where you have your OpenMP offload region, and within there you're doing some HPC, some kind of specific computation that you normally find with HPC science codes. This might be a fast Fourier transform or some linear algebra operation where you're multiplying two matrices. So there are many libraries provided by ROCm and NVIDIA SDK that allow you just to use an off-the-shelf subroutine. But when you do that, the parameters that you're passing in, you need to indicate to the runtime as well as the compiler where those parameters actually exist. Which memory are they in? Are they in the device memory? And so here's an example of that. Suppose we have a variable var underscore a. It's already been mapped to the device within your target construct. And now you're going to call a CUDA or a HIP matrix multiplication subroutine that's taken from a library. And you want to avoid any reallocation of memory on the device or repeating the transfer of data from host to device. So what you do here is you use a clause that you add to your target construct, and that's use underscore device underscore ADDR address, and then in between the parentheses you can pass a list of variables, and you're saying these variables have device addresses, and you are to use those within the target construct. So here's this example, but more fleshed out. So if you just look at the, in all of these code examples, there will be a C version and a Fortran version that does the same thing. But looking at the C, you can see that there are two target constructs. There's an outer one where we're actually mapping 3 arrays, and these arrays are involved within a call to a dgem matrix multiplication operation. So what's happening here is that A is being multiplied by B, and then C is being added, and then the result is being returned in C. So we've got a situation where we're in an OpenMP region. We've already mapped the data to the device, and then when we actually call the rockblast dgem subroutine, we want to tell the runtime, the compiler, that we are using arrays that are already on the device. And you see the Fortran is much the same. We can have another situation where data or memory has already been allocated on a GPU, and then subsequent to that we're going into an OpenMP region, and we need to then indicate to the OpenMP region as opposed to the ROCm subroutine that memory is already on the device and you are to use the data located there. This kind of scenario that I've just sketched is very useful if you already have an OpenMP code. So this is where a loop, the iterations of a loop, may be assigned to various OpenMP threads, but everything is running on a CPU. Now you're transferring to a GPU, and the data that this loop is using, you basically do a HIP allocation for it so that it's allocated on the GPU. When you come to your OpenMP region, you want to change things as little as possible. So you can just add in an extra clause called this is device pointer clause. And then you pass in the list of variables that you're indicating are located on the GPU device. So this avoids having to accidentally map data more times than is necessary. So here's a C example where we're just doing 2 HIP looks for 2 arrays located on the GPU, B underscore device and C underscore device. Then when we go into our target teams region, so we are distributing the iterations of this for loop over various GPU threads, and each one will be assigned to a core that's part of a compute unit on the GPU. So we're just saying C underscore device and B underscore device are located on the GPU already. So there's no need to do a mapping from any host equivalent arrays to the device. Now with the Fortran example of this is a little more involved here. So we've got actually 2 types of pointers. We've got C pointers for the language, for the C language, and Fortran pointers. And so when we're using the HIP malloc subroutine calls, we're passing it C pointers in there. But because this is a Fortran code, and within our actual Fortran OpenMP region, we're using Fortran pointers, and you need to have a conversion from the C pointer to the Fortran pointer, and this is the point of the C underscore F underscore pointer subroutine call. So in Fortran, things are a little bit different as regards pointers, in that a pointer to an array will point to an array descriptor. So not only is it just pointing to the address of the first element in the array, it's also pointing to other information such as the size of the array, that's what the descriptor contains, and also the rank of the array, and also the sizes of the dimensions of the array. So this is why we have a need to convert from a C pointer to a Fortran pointer. But otherwise, the principle is the same. We use the is underscore device pointer to indicate that everything's already on the device. So that's that section. Are there any questions so far? If not, then I'll carry on talking about custom data mappers. So far, you would have seen an OpenMP example where you just do a map of a base type. It might be an integer or an array of doubles, something like that. But what if you want to map something that's more complex, that's a heterogeneous data type, in that it contains more than one base type? So a structure is basically what I'm talking about here. And we've got two examples which are the same, really, but they use the different syntax that you have for C and for Fortran. So this is a structure that contains 4 fields. So it's a size integer, n, and then 3 pointers to arrays. And then, so we can call these structures, we can give it a name of our choosing. So we've got my_struct for our C example and my_type for the Fortran. And what you would have to do if you were doing this every time you are needing to call a kernel, say, that is going to use these arrays, before that, you would need to map the data. So you would take an instance of your data type and you would have to map explicitly each field within the data type. So that's what's happening here in these 2 snippets of code, C and Fortran. So we laboriously have to say that each of those 3 arrays need to be mapped, and we need to specify the size of the mapping of these arrays. So that's quite a cumbersome thing to have to do every time you need to run a kernel that uses those arrays. So it is possible to just do it once only. So you declare something called a custom data mapper. So you'll use this pragma directive OMP declare mapper, and then you pass in the name of your data type, and then you just give it a dummy variable for an instance of that data type, and then you can proceed that with a map clause, which then explicitly defines how each of the fields within your custom data type are going to be mapped. So here's an example of that. So you declare your mapper, and in the declaration of the mapper, this is where you have to explicitly say each field is being mapped like this. But then subsequent to that, when you go into target data regions preparatory to invoking the kernel, you can then just treat the mapping of your custom data type as if it's a base type. So you just refer to the variable name of your my_struct, and it's as straightforward as if you were just mapping a base type. Yeah, you can see it's the same for the Fortran code as well. In Fortran, you just use a different character to indicate the fields, the percent rather than a dot. So that's that. I take it that's quite a straightforward section. Does anyone have any questions? I can hear there was one question. How to map an already filled stub vector or an array. I'm not sure about that. I don't know if Luca knows, but I don't know if there's a mean of updating what you've done. Because you've got a custom mapper already, you can do an update. When you do, I think if you do the two, if you use an OpenMP and you do the 2, that's automatically going to bring in the new values. Is that right? Because you've already defined the yeah.
Yeah. So there's nothing special about a CD vector CD array, as in there are contiguous set of data. So you'll do it the same way you would if you had a pointer, like a normal pointer arrays with a pointer, but you pass in as address, you pass in the address of the first element. And that will work because all the data inside std vector or std array is guaranteed by the standard to be contiguous.
Okay, thanks, Luca. So now we're talking about different types of memory that you need to be aware of when programming GPUs. And there are three types we're going to cover here. There's pageable memory, and pinned memory, and unified memory. So pageable memory is what you're used to when you allocate code, when you allocate memory within code that's running on the host. So pageable means you get a virtual address that exists within a virtual page, and so you are isolated as a programmer from what's going on under the hood, from where that data is actually being stored within the memory hardware. And then the operating system will control the way your data is being paged. You have pinned memory, and pinned memory is basically fixing a memory location such that it can then be transferred to the GPU. I'll explain more about that in a moment. And we have unified memory. This is memory that is accessible from both the host and the GPU device. Now, unified memory can be implemented in software. So if within device code, it's attempting to refer to data which is currently located on the host, the runtime will step in and notice that, and then under the hood, transfer that data so that it's actually on the device. So it will do a mapping, in other words. Unified memory can also be done in hardware. So for the latest GPUs that are available, there is memory that is accessible directly from the host and the device. So having that situation, it removes the overhead of the programmer needing to know where data is actually resident at any point in time, and then to make steps, if necessary, to ensure that that data is in the right place. So if it's unified memory, as a programmer, you're free from having to worry about that. And if the unified memory is implemented in hardware, it's going to be quite efficient too. So I just heard a question there. So at the moment, Luca, is it possible for you to tell me what the question is? I had something posted in the chat because I can only see my full screen at the moment.
It's already answered. Just
okay, thank you. Okay, so looking at pageable memory. So when you allocate some memory, you get a virtual address, and where that actually resides physically, you don't know anything about as a programmer. That's handled by the operating system. So it could be that that actual piece of data, the memory that's holding that data may be located on a particular DIMM strip, a piece of memory, and then at a later date, the operating system may decide to transfer that to another part of the memory hardware, and it may do so in order to make it convenient to manage all the different tasks that are running on the host at any one time. Having a virtual address space is useful because you can work with an address size that is larger than supported by physical memory. So adds a layer of convenience, and it's also obviously as the programmer, you don't have to worry about the details of the physical memory that exist on the computer in which you're running the code. If there's too much data to be held in memory, then the operating system can step in and move data to the hard disk if necessary. So you have the situation where you have like a page lookup table. So there will be a lookup table that relates the virtual addresses to the actual physical addresses of where that data actually is on the memory hardware, and that's managed by the operating system. And so yeah, and this is accessible from the host. It's just a summary of what I've said. But when you need to transfer data to a GPU device, you need to be careful because the GPU doesn't have access or direct access to the host operating system. So the GPU won't know about the virtual addressing that's in play and the fact that data may migrate from one place of the memory hardware to another place. So we need to at first lock the page. In other words, we need to make sure that the memory that we're about to transfer to the GPU is pinned, in that the operating system isn't going to move that to another part of the memory hardware, or to maybe move it to the hard disk even. It's going to remain fixed, which is necessary, because then we need to be sure that then when the data is transferred to the GPU, it remains there during the time of the transfer, so that all the data will move to the GPU as expected. So when you're in your OpenMP code and you do a map, there's actually 3 steps that are taking place. If you were mapping an integer array, there's actually 3 steps that are performed. The first step is the allocation of a pinned array. So you have your pageable array that's already on the host that you want to map, the contents of which you want to map to the device. So the first step, you allocate your pinned array. The next step is that you transfer data from your pageable array to your pinned array. So all of this is happening on the host, and only then are you ready for the last and third step, which is the transferal of data from your pinned array to the array on the GPU. So there's quite a bit of work that needs to be done. But it is possible to specify, I think, well, for some compilers, the way they've implemented OpenMP offload, they do allow you to indicate that the data being mapped is already pinned. So when you declare an array on the host, you can say that it's pinned, and that means that when then that array on the host is populated by the host code, because it's already pinned. When you then subsequently do a mapping in preparation to going into an OpenMP offload region, because that data is already in a pinned array, then the transfer can actually happen faster than it otherwise would, because you've done up front the first 2 steps of the data transfer. So here's just a schematic giving you again an overall picture. When you are running code, part of which is offloaded to a GPU, you've got 2 memory hierarchies in play effectively. You've got what's on your host, where you have a virtual memory, which is paged, and then but underneath that it'll be supported by actual memory hardware, so a dynamic random access memory in this case. And then on our device we have another memory hierarchy. So when we've mapped the data across, there'll be a virtual memory address for that, and the supporting memory and hardware will be something like high bandwidth memory. So in looking at unified memory now, you've got a situation here where the unified memory is actually being implemented in software. So the details of mapping are being hidden from you and done automatically by the programming framework, be it CUDA or HIP. I mean, it will be something what OpenMP sits above. And so in this the diagram here, we have a pointer to an array of doubles, and it's currently paged on host memory. So if we then go into a bit of code, some offloaded region that's attempting to access that same array, the runtime will notice that actually it's on memory that's on the host. So we need to do a mapping before that code can proceed. So that's done automatically for you. So it will be mapped to memory in the high bandwidth memory that's resident on the GPU device, so that then your offloaded code can work as expected. So in OpenMP, you can have a directive up front where you say that you're going to use unified shared memory. And you, as a programmer, the advantage of doing this is that you don't have to worry about mapping. You don't have to worry about if data is already resident on a GPU, already has the up-to-date values in the array. But I'm not sure the support for OpenMP unified memory. You may need to check that it actually exists by reading the compiler manual. and it may not work for older devices. So for you need a device that's as recent as an Ampere 100 if you're using an NVIDIA GPU, or a MI210 if you're using an AMD GPU. If you're using the very latest GPUs, that's when the unified memory is implemented in hardware. So you have separate memory that's accessible from both host and the device, and you've got a reasonably good bandwidth for both the host and the GPU, so performance should be good for the very latest GPUs. So now we'll talk about memory on the device itself and how that is organized. So the massive parallelism that's provided by a GPU is in the form of compute units. We were talking about an AMD GPU or an NVIDIA. They refer to these as streaming multiprocessors. So each of these compute units can be thought of as a mini compute node. It will have a certain number of cores, maybe 16 or 32, and there will be memory that is local to each of those compute units, and it will be in the form of registers or a cache or actual memory, shared memory. It's usually not very big, so of the order of 100K or so. But then there is also global memory, or global to the GPU device, that is accessible to any GPU thread, no matter which compute unit core it is running on. And so global memory is normally in the tens of gigabytes. So that's just a summary of the different types of memory. On the device, you would expect that there's more global memory, but it's slower to access compared to the memory that's local to each compute unit. And on the host, you have pageable memory, which is the type of memory you deal with by default, which then any data you want to transfer to the GPU must first be transferred to pin memory in order for before the data transfer can proceed safely. So that's the section just covering the different types of memory. Are there any questions about that? No. Okay. So I'll move on to how it's possible to control the allocation of memory within OpenMP. So what you can do is you can define a number of hints. So you can you can at first declare what memory space you wish to use, and then also you can indicate how you want the memory to be allocated, and you do this by specifying a number of allocated traits. Now, as regards memory space, you could just use OMP default mem space. So you're asking the compiler to choose for you. But there are various options here which you can check in the compiler manual to see the level of support that it has for OpenMP. You've obviously, OpenMP itself is a standard, is an API. So that you will need to use a compiler, and the level of support that a compiler may have for the OpenMP standard may vary. So you need to check in the compiler manual also to see the range of different memory spaces that are supported. And so the various options, which aren't listed here on the slide, but you can do things like you can say, I want to allocate memory that is a high capacity, or I want to allocate a memory that once I've written the data to this memory will subsequently be read-only from that point on. So that's constant memory. You can specify memory that is a high bandwidth, or memory that has a low latency. And I'm guessing what counts as low latency or high bandwidth will be system dependent. There are also allocator traits, and so here you would specify how the memory allocation is going to be done exactly, and you can specify if there are going to be any restrictions as regards accessing that memory. Now, these traits can be thought of as hints, and the compiler may accept them and compile your code, but it may ignore them. And so the way to check, as I've said, read the compiler manual, but also maybe to profile your code to give you an idea of what's going on under the hood, to make things to check that your hints are being respected. So here's a slide that just covers the various allocator traits. So you can specify how the data is aligned. And so if you're allocating something like an array or an array of structure, an array of structures, each data item will have a certain size, and you might want to make sure that each data item is stored such that it respects the word boundaries. So a word is sort of how the is a unit of memory, so it might be 16 bytes or 8 bytes. It depends on the system you're using. You want to make sure that your allocation of memory respects word boundaries. You want to avoid a situation where a particular data item doesn't straddle a word boundary, which means that when you then do a memory access, it requires actually 2 memory accesses for both words over which the data item is being stored. So you do that by, you would pad the memory that being allocated. So each data item, an element of an array, for example, will be sitting with, can be obtained via a single memory access. So when you align your data, the memory accesses are faster, more efficient, but the cost of that is that you are using more memory. And then you've got various ways in which you can control, you can specify how that memory is going to be accessed, whether or not any thread can access the memory, be it on the host or on the GPU, or whether it's private to the thread. So in other words, each thread has its own copy of that memory. And then you can specify it in terms of a group of threads accessing a particular area of memory. So a P team will be the group of threads that are assigned to a single compute unit on a GPU. And for a C group, we're talking about a contention group. So we may have a group of threads that are combining to do a piece of work which requires some synchronization. So these are the threads that will need to synchronize on a hardware resource, maybe a software resource such as a lock, to make sure that the work is being synchronized correctly. So C group will be something that probably applies more in a host environment rather than a GPU. And then we can also specify if that memory is going to be pinned or not. So I've already explained what pinned memory means. So here's an example of what we're doing, what I've just talked about. So we, again, we've got C and a Fortran version, but I'll just talk about the C. So here we're declaring which mem space we are going to use, and then we'll specify our array of traits. So we're specifying that we're going to be using pinned memory, and then we're having a 128-byte alignment for our memory allocation. And now we will specify our own custom allocator. So we're using the OMP init allocator subroutine, and within that we pass the memory space that we've defined, as well as the array of traits and the number of traits. And it's the same kind of thing that we do for the Fortran code as well. So then when we come to use that, we've defined then a custom allocator which specifies a memory space and the traits that we want to use for subsequent allocations for particular arrays. And we indicate which arrays or which data structures using the allocate directive. And to that allocate directive, we'll name the allocator that we've previously defined, and then we'll list the variables that we want to allocate using that allocator. And here's just a simple example of that on the host. So we're just using the OpenMP allocate, and we're allocating a double array called B. And so we know when that array is allocated, it's going to respect 128-byte alignment, and it's going to be pinned, so that if it's subsequently mapped to a GPU, that's going to go a little bit faster than it otherwise would have done. And then we're also just using the default memory space, whatever that happens to be. So for the host, it's pretty much the same thing. We have a slightly different approach within our target construct. We have the uses underscore allocators clause. So, and in between the parentheses for that clause, we pass our previously defined allocator, my underscore allocator. And then when we're doing any mapping or allocation of memory that's directly on the device, such as used by this map alloc call here, we indicate via the allocate directive which allocator we're going to use. And then in the Fortran example, it's a little bit different here. In now within our target region, we're specifying the number of teams that we are going to use. So each team will assign to a different compute unit, but each team is doing the so I'm not sure what work it's doing. I think it's going to be on the next slide, but we're specifying that our C array is going to be private to each team. I think that's right, rather than private to each thread running on each team. And then we do the memory allocation per team. So this slide, we're talking about the local data share or store. So this is memory that's accessible to a threads running on a team, those threads that have been signed to a single compute unit. So on the AMD GPUs that you have access to, I think there's something like 104 compute units. So that's how you get the massive parallelism when you offload to a GPU. There's just lots of independent groups of cores that you have access to. You can provide, so there's no direct, I don't think there's a direct way within OpenMP to say that you wish to use memory that's local to a compute unit. You can provide hints. There are compiler extensions apparently, but obviously you're restricted to a compiler if you use those. So here's an example of what might happen if you. So in the C example, we've got a target region. We've specified 4 teams. We've allocated a C array. Now, where that actually gets allocated on the GPU depends on the size of block size. So if it's small enough, then it can be used it can be allocated in the shared memory. If not, it will have to go into the global memory. But then continuing to look at the code, you've got our for loop. So the iterations of that loop will then be divided amongst the threads that are running within each team. So I think in this case, each team gets the same loop. So you're duplicating work, but this is just as an example for clarity. And you've got the same thing within Fortran, but it's just a bit more different. Just slightly different in that the loop is in its own subroutine. So within the target region, you're calling the loop subroutine. So here is how you might provide a hint that you wish to use memory that's local to a compute unit. So at first glance, it looks quite cumbersome. So if we go back, we've got our array on the host we've declared as block size, and then we're going into a target construct. We've got 4 teams. We've said that our array is going to be private to each team, and then we're specifying that we are going to use a number of allocators. We're only using one. We're using our PT mem alloc, which is something that's already provided, and then we're specifying that we're going to allocate on the GPU our C array of size block size, and then we need another allocate clause. And what the allocate clause is basically saying which allocators we want to use with which variables. And so here we are going to allocate the C array within the memory that's local to a team, that's local to a compute unit. And so this is probably fine if within the loop we're just updating, if each thread is updating its own element of the array. That's okay because you won't get a race condition between threads. If a thread only accesses its particular index position. And then the Fortran is much the same. So we've got this need of specifying which allocators we intend to use within an offloaded region, and then which variables are going to be allocated on the GPU, and then we have to add a allocate clause, which basically says, we're using this allocator for that variable, and so on. So you can have more than one variables using different allocators if necessary. So that's a fairly long section. So are there any questions about that anyone wishes to ask? Okay, I can't hear any popping sounds coming from the chat, so I assume everything's okay. I'll just move on to the last section to do with asynchronous offloading. So previously, if you've done any OpenMP offload exercises, you would have mapped data preparatory to invoking a kernel that then does work on that data. And everything so far has been synchronous. It's been blocking. So when you go into a Teams construct that's mapping some data to the GPU, control doesn't pass back to the host immediately. The host is blocked until that completes. As we're doing a data transfer, it's the same with when you invoke a kernel. Now, it's possible to make such operations non-blocking by using the no-wait clause. And when you do that, it means control passes to the host, and the host is free to do its own computation somewhere else, or it's free to invoke another kernel that runs on the GPU. But at some point, the host needs to wait at a barrier so that it knows from that point on the work that was being done on the GPU has completed. Now, when you schedule work, when you launch work asynchronously, it may be necessary to specify depend clauses. You may need to indicate that, okay, I'm saying that this work can run straight away, this kernel can run straight away, but actually it can't run until this particular array has been mapped to the GPU. So you'll see examples like that in the coming slides. So here's just an example of we've got a target construct. We're mapping two arrays. We're copying two arrays to the GPU, XSI and YSI. We specified a no-wait clause, which means that the host won't block. The host will immediately go to calling a subroutine called myHostComputation. So that's great. But then after it's done that, and it then has to wait for some reason, because there isn't a from clause on that map, but never mind. So, when it goes to the OMP task wait, once it's moved on from there, you know that the data transfer has completed. So you can, as well as using no wait with a data transfer, you can also do the same thing with a kernel invocation. So that's what's happening here. So the computation A on device loop, the iterations of that loop will be assigned to various GPU threads that are running on compute unit cores. But if you've used the no wait clause there, control passes back to the host so that it can do some other computation. So in this case, it's actually going through its own loop. It's all very straightforward, all very similar between C and Fortran. And again, we have a OMP task wait, which once we've moved on from there, we know that the loop, the computation A on the GPU has completed. So what you can also do is use the no wait clause to allow the host to run multiple kernels on a GPU at the same time. So here's an example of that. So it may happen, it could happen that actually each kernel, which I'll refer to as kernel A and kernel B, they may actually execute serially, one after the other. It depends on how much hardware resource is available on the GPU. It depends on the value of M, in this case, M being the number of iterations in the loop. So on a NVIDIA 210 that we have on ARCHER2, sorry, on the AMD MI 210 that we have on ARCHER2, that's something like 104 compute units. So if M is 204, for example, or 208, then you have more iterations than there are compute units. So it's likely then, I think in this case, that the computation A loop will be called and will run before the computation B loop does. But if M is, say, 52 iterations, then there's no reason. There are sufficient compute units on the GPU in this case for both computation A, both kernel A and kernel B to run at the same time. And in that scenario, the two loops will take less time to complete. You're able to use the parallelism there. The parallelism available is such that the loops can run at the same time. And then you have a task wait to let you know when both kernels have completed. So you can also specify various dependencies here, and you can specify the direction of the dependency. So you can have an out, an in, or an in-out. So when you have some region of, if you have some operation, it may be a kernel invocation or a data transfer, and you have an out dependency, what you're saying there is that there is a subsequent data transfer, or there's a subsequent kernel invocation that needs this variable that's listed after the colon before it can start. And then corresponding to that, mirroring that, the subsequent kernel that's being called would specify an in dependency on the same variable. And then if the kernel is part of a chain of kernels that you are calling, so a pipeline, in other words, you would specify an in-out and an in-out dependency. It's relying on the kernel that's being called before, writing values to X, and then the kernel that comes after it is going to need the values that this middle kernel is going to be computing. So here's an example of that in C of just what I've explained. So we have our target construct that is mapping an X array to the GPU, and we're saying that there's going to be a dependency. So let's the compiler know, let's the runtime know that there's going to be a kernel invocation that will require this X array to be on the GPU before it can proceed. So this is in the bit of code that's iterating over a loop. But obviously the iterations of this loop will be done in parallel, assigned to various GPU threads. But we're saying that we're dependent on this X array first being written to the GPU, and also there's going to be another kernel invocation that's going to rely on the output or the new values that we're providing for the X array. So you see that now it's kind of identical, but because there's no kernel invocation after the second one, it's just an in dependency here. So this again, we're kind of wanting to give an example on one slide showing the different dependencies, and for clarity, we've done it like this. It doesn't really make sense as actual code because our no wait clauses are basically made redundant by our dependencies, but we might have a situation here where the data mapping is mapping several arrays, and actually our kernel that comes after it is only dependent on one of those arrays. So once that's been mapped, and then you're moving on to mapping the other arrays, the kernel can proceed and we can execute that. Or there may be other kernels that we're calling that don't have dependencies, so those could be running on at the same time as the data mapping. And here's the same thing, but in Fortran. So here's so the summary. What we've talked about here is how your OpenMP offload can be done alongside GPU programming frameworks such as HIP and Kita. And then we talked about custom data mappers that you might want to do when you want to map heterogeneous data structure to the GPU, and how to do that conveniently, so you're not having to explicitly specify the mapping of each field every time. Then we talked about the different types of memory that you need to be aware of when using offloaded or GPU accelerated code, how you can control the memory allocation, and then asynchronous tasks lastly. So that's the end of the talk. Are there any questions? So everything's quiet in the chat. So I guess everything's okay then. That's all quite clear. Thank you, Felica, for providing those slides. Do we want to take a break for 5 minutes, and then I think there's a presentation after this on performance.
Yes, I would say we take a 5-minute break.
Okay.
And then in 5 minutes we're going to talk about performance.
Okay, thanks.
Okay, everyone. Can you all see my screen?
Looks okay to me.
Perfect. So we're now going to talk about, we've seen some of the basic concepts on how to use OpenMP for offloading, and also some more advanced topics. Now we're going to talk about how to make your code fast using OpenMP. It's very easy. If you've ever written OpenMP before and you run some similar example, and you run it, you probably found, there's a good chance you found that your code runs slower than on a CPU thread. But because you need to be careful on how you map your problem to a GPU in a way that is effective in order to use all the computational performance of a GPU. So we're going to cover various topics. So one is occupancy. Essentially, we want to make sure that we fill the GPU, we offload enough work to the GPU to keep it busy. Then I'll explain to you why branching, which means having a lot of if clauses, is really bad for GPU. And we've talked already about memory, but this time we'll talk all about how and why you should use memory in an efficient way when using a GPU. And we'll finish with a few miscellaneous topics. Okay, so occupancy. We've already talked about GPU devices have high latency but high bandwidth. So that means that it takes a very long time to start an operations, but you can get a lot of work done in very small time if you launch it enough task to the device. So you need to have enough task to fill all the memory and compute units which are on the GPU. Essentially, what you need to do is you need to have enough task on the fly, so enough work that you can exploit of the bandwidth and hide the latency of a GPU. Now, in the remainder of the talk, we'll use the AMD MI210 as an example. So if you have access to some other GPU like NVIDIA, the specific numbers will be different, but the concepts are exactly the same. So we're using this GPU, which is the one we have on ARCHER2, just as an example. So the MI210 has 104 computing units in AMD lingo. So we talked about computing units the previous week. So these are the units that essentially are doing the work. So they're the ones doing all the floating point operations. Each computational unit has 4 theme processors. So there are essentially 4 units that can compute floating point operations on each computing unit. And each one has 16 lanes. So that means each theme processor can essentially process 16 data items at once. At maximum, everything on a GPU executing groups of threads, and for AMD this is 64 threads. So this is called a web front. If you use NVIDIA, that would be called a warp. So on NVIDIA there are 32 threads, but AMD GPUs use 64 threads. And on the MI210, you schedule up to 8 web fronts to each themed processor. So 32 per computing unit. Remember that all the threads in one web front, while they can operate on different data, they all need to execute exactly the same instruction. So that means you have a lot of parallelism on the GPU. So you have, as an example on this MI210, you have 104 computing units. Each computing unit are 4 processors. Each one can deal with up to 8 instructions per processor, and each instruction executes on 64 threads. So in total, that's about 200,000 threads that you have on MI210. Now contrast that with a CPU. For instance, the ARCHER2 node on the CPU, you can have 128 cores. So there's no point in having more than 128 threads on a CPU. On a GPU, instead, on MI210, you want at least 200,000 threads being sent to the GPU. If you have less than that, you won't be able to fill the device. So you won't be using it efficiently. You're wasting a lot of the resources. Even worse, you might not have enough parallelism to hide the latency. So the ratio between the number of threads that are executing in parallel on a GPU and the maximum number of threads that can be scheduled on a GPU is called occupancy. So in general, whenever web front is sent to a GPU, often they'll be stalled for lots of block cycles. For instance, they need to access some memory. Doing computation nowadays is like floating point operations are really fast. But in order to do floating point operations, you need data to operate on. And the data can take a very long time to arrive. So that means the web fronts are stalled. So while they're stalled, what the GPU can do is they just switch over to a different web front. So if a web front is stalled because it's waiting some data from memory, it can switch to any other web front which is on the device. as long as it's ready to execute. And because it can switch so quickly between different waveforms, something the CPU cannot do, it can add the latency. So that's why you need to fill the device with as many waveforms as you can. Now, you don't always need 100% occupancy. You just need enough threads on the device to add the latency. So that means having higher occupancy does not always mean that you have higher performance, especially if your changes gives you higher occupancy, but harms the performance in other way, for instance, how efficient you are at using memory. So what can limit occupancy? Well, the first thing is you need to give them enough tasks. So if you offload it with OpenMP, that means you need to have enough teams. So ideally, you want at least one team per computing unit, and that means that on most devices that will be something in the hundreds. So mine 210 is 104. You also need your teams to be big enough in order to use all the thread. So team size, number of team will affect your occupancy. It's not just the total number of tasks, but also over distributed between teams and essentially the iterations in a parallel for inside the team. Another thing that can limit you is shared memory or the amount of memory on the local data store. On OpenMP, as we've seen, it's a bit difficult to use. There are ways you can tell the compiler how to use shared memory, which can be much faster. But often OpenMP program will not use efficiently shared memory. And finally, another resource you can run out of is registers, which we'll talk about more later. So each team is scheduled to a single computing unit. Okay. So as I said, we need at least as many teams as computing units to fill the GPU. And each computing unit can handle up to 32 waveforms. You need to make care how if your teams fit well inside the computing units. For instance, if you have a team size which is 17 waveforms, so each team has 17 waveforms. That means that you can't have two teams scheduling on the computing units because that will be more than 32 waveforms. So you can only have one. So you can only use 17 out of 32, that gives you an occupancy of 53%. While if you were to have just one less waveform, you might be able to achieve 100% occupancy. So how can you control this? Well, first of all, number of tasks. Make sure that you have enough parallelism, so that you have enough iterations inside your loop to spread over the GPU. You can control how many teams you have with num teams. So this only gives you an upper bound. It only gives you an upper bound of the number of teams inside. And the other clause is threadling, which kind of does the same thing, but for the number of threads inside a team, or if you want the number of iterations inside a parallel for loop. Other ways, so yes, make sure there's enough parallelism. That's usually the first thing about getting good performance on GPU. Another technique could be if you have several loops, try and merge them into a bigger loop. So that's a way to expose more parallelism. Also usually collapse clause. So if you have a multidimensional loop, you don't want to spread your threads only using the outer loop. So you want to collapse the outer and inner loops into one giant loop. So you can increase the amount of parallelism. So this is very similar to what you can do with OpenMP on CPU as well, but it's particularly important for the GPU. Another term is to look at after is occupancy, is register pressure, which means every team, in order to execute, needs a certain number of registers. So registers are memory locations on the processor which need to store enough information for doing all the operations. So all the data you need to load from memory eventually will end up on a register. If your team needs a lot of register, you might run out of a register on the processor, and that means your team cannot be scheduled. This is a fairly common one. So it's fairly common for kernels to be limited by register pressure, which means not enough registers are available on the processor, so teams cannot be scheduled. So in particular, the manage are two types of vector registers, so vector registers and scalar registers. So vector registers hold 64 items, each 4 byte wide. And there are up to 512 vector registers per processor. Scalar register is similar, but the difference is that while the vector register will hold an item for every thread in a web front, so that it's a different item per register, per thread. A scalar register, they all access the same value. So all the threads in your web front are reading the same value. So there are up to 800 scalar registers per processor. As an example, suppose a web front needs 128 vector registers, but we only have 512. So that means that we can allocate only 512 times divided by 128. So that means 4 web fronts per processor. We have 4 processors, so that means we can only allocate 16 teams on a computing unit out of 32. So we get an occupancy of 55%. So how to remedy this? Well, if it looks like you're suffering from register pressure, something you can done just by using vendor-specific tools. So the NVIDIA tools can do it, and the AMD tools can do that as well. So one way to do it is if you have a very big loop, very complicated, just split into smaller loops. That's not always trivial. So that might mean you have to create some temporary arrays to paste data, to forward data between different loops, which might harm how efficiently you use the memory. Another way is to use the thread limit clause. Essentially, more information you give it to a compiler, the more efficiently it can use registers. So if you tell it that there's an upper bound on the number of threads per team, then it can manage registers in a more efficient way. And there's a fixed amount of shared memory per compute unit. So if your teams have too much shared memory, they can limit your occupancy. Fortunately, in OpenMP, that's rarely a problem. Any more questions about this? So if you want to take one message out of it is make sure there's enough parallelism, have enough stuff to fill the GPU. So the other things we're going to look at is branching, which means when you have part of your code where there's a if statement, and some of the threads do something, and some of the other threads do something else. However, on a GPU, all code runs in groups of threads, so one web front. And for the AMD, there's 64 threads. So you always have the same instructions executed by 64 threads. So what happens if in your code you have a if branch and you're telling half of your threads to do something and half of your other threads to do something else? For instance, in this example, you may have that on a web front, half of your threads are operating on the even, so they're setting all the even values to A and all the odd ones to B. Okay, so this is a cartoon representation. So every square here is an element into the array. And we set X to A on all 11 threads and to B on all the odd ones. However, because we can't, the same instructions need to be run at the same time everywhere. What the device does is it does some masking. So essentially what it does is it executes the instruction x of e equal a on all the threads, but then it masks out the result on all the odd ones. Okay, so the black ones are doing the same instructions, but they're masking the result. So nothing is happening. And then you do the same things for all the odd threads. So all the odd threads will be setting the value of a corresponding element in the array to B. They're doing the same on A, but they're masking out the result, so it doesn't change anything. As a result, instead of doing one instruction, you're doing 2 instructions per thread. So this is not a problem if you only have a few if loops here and there and only affect some of the threads. But if there's a lot of if loops and each of the threads are doing something completely different, that can destroy your performance. So a typical example would be Monte Carlo code. So you might think of giving each thread a different particle, and then each particle goes through some random set of events. But because they're random events, every thread will be executing bits of code, and you end up with your code being serialized. So essentially, you're effectively only using one thread at a time on the whole device. So the performance is terrible. That's one of so this can limit the use of GPUs for some applications. Does not mean you can't use GPU, but you might need to rethink your algorithm. An algorithm that works well on the CPU is not necessarily an algorithm that works well on GPU. So best way to avoid the problem is to just have the threads all do the same thing or nearly the same thing. Having an extra instruction is not going to change much, but having completely different functions running on different threads, that's going to kill your performance. So you might want to think of your code. Any doubts or perplexity? Okay. Let's move on to how to use memory efficiently. Now we've talked about memory a lot. Now that we've said of different types of memory on the device last week. So that's global memory, accessible by everyone. There's memory, that's the L2 cache, which is a faster memory but much smaller, which can be shared by a group of computing units, and L1 cache, which is shared only by threads on the same computing unit. And generally speaking, all this, the faster is the memory, the smaller it is. So you can't save all your data on there. So global memory is the slowest, and typically can handle 300 gigabytes. The L2 cache is much faster, but much smaller. It's usually 10 megabytes per group of computing units. On the remaining 210, this happens to be all of them, but on other devices, it might be just a subsection, but a significant fraction usually. And then there's the L1 cache and shared memory, which are essentially very similar, and on some devices like NVIDIA, they're actually physically the same hardware. The data on the L1 cache is only visible from threads on the same computing unit, and it's fairly small. It can contain up to 60 kilobytes per computing unit. So how does the process work for accessing data from memory? So initially, you move all your data from the CPU to the GPU, so it ends up in global memory. And then data needs eventually needs to end up on the chip, so it needs to end up on registers. All data you access will eventually end up on a register on a processor. In order to go through that, every time you look up some data which is in global memory, essentially the register first look in the L1 cache because it's the fastest. And if it's not there, it will look on the L2 cache. If it doesn't find it there, it will look on the global memory. Hopefully it will be in global memory, and then it will copy it over to the L2 cache, and then copy it over to the L1 cache, and then finally on the registers. So every time you're traversing all these layers. Because it takes quite a long time to do all these data movements, it's much more efficient if instead of operating on just one byte at a time, you do it on a group. So this is a group of contiguous data, and we call that the size of that of this array is called a cache line. So a cache line will typically be 64 bytes or 128 bytes. For example, NVIDIA A100 has 128 bytes cache line, while MI 110 is only 64. Now, this is important because if you have different threads in a web front all access the same cache, then they all need to do just one load instructions. Remember, the instructions are shared by all threads, so essentially, one web front will run one load instructions, and you have all the data available for your threads. So that means, generally speaking, you want to reduce the amount of traffic between all these layers, and so reduce the number of cache lines that are moved around. Essentially, that means reusing memory you've already used. So if you've already accessed some data recently and you reuse it, that's likely already in the cache. Also, if it's close partially, which means it's data you haven't used yet, but it's close to something you have used, it likely ends up in the same cache line, so it's already been moved to the cache already. So the process where you have several threads that manage to reuse data which is on the same cache line is often indicated as collapsed memory access. So let us take this simple example where we are essentially summing, taking a vector, summing to another vector plus a constant, so fairly easy. And we do it for every item. Okay, so let's look at one web front. So suppose we're on AMD, so we have a web front of 64 threads. So each thread needs to load one element from global memory. Okay, so thread number 0 will have number 0 in the array, number 1 will have the data in a position at the index 1, and so on. There are doubles, which means on a cache line you can fit 8 values. So that means that for 8 threads, they're all accessing data which fit on one cache line. So you don't need 8 load instructions, you just need 1. So you do 1 load instruction and you transfer 64 bytes. So you only need 8 load instructions per web front. So overall, each web front is doing 8 load instructions. Each load is 64 bytes on IMI 210, and that gives you 512 bytes. So you have transferred 512 bytes from global memory. Now let's do the same, but let's do a stranded access, which means we're summing the value of B in E times 8, and we're adding a constant. So at every iteration, we access contiguous element in A, but we skip by 8 on B. So that means the first thread will access the element number 0, which is on the first cache line, and thread number 1 will have to load B from index 8, which happens to be on a different cache lines. So every thread will need to access data from a different cache. So that means you need 64 load instructions per web front. So each thread is doing its own load instructions. So in total, you're transferring 64, you have 64 load instructions, times each instruction will load 64 bytes. So that's about 3.9 kilobytes. That's way more than the 512 bytes when we were doing contiguous access. Now, in OpenMP, we don't just have contiguous loop. We also have nested loops. So if you want optimal data access, so you want to make sure that all successive threads, which are all on the same web front, access contiguous elements, so without jumping over, the best way is to make sure that successive iterations of the inner loop access contiguous data on the thread. And then you make sure that the two interactions are merging together by using a collapse curve. Okay, so this is an example. So we're in this case it's an example with C and C++. So here we have two loops, and the outer loop is a loop over E. So over the rows, and the inner loop is with J. Fortran similar, but with the order, we have the order of the loops different. Now, if you have in C++, you probably know that elements are stored highwise, or if you prefer, the last index is the one that runs the fastest. Which means if you add 1 to J, you're accessing contiguous element. The inner loop is in J, so great, memory access are coalesced. But if you edit the other way around, like this, then element of, if you have equal 0 and equal 1, then you are accessing data which is not contiguous in memory. And that means you're skipping over, which means you're not using memory as efficiently. So make sure your loops are in the correct order. If you're in Fortran, the same thing, but remember the Fortran allocates data when you have a two-dimensional array in a different, in the opposite order, which means it's stored by column. So you prefer the first index is the one that runs the fastest, which means element with E and E plus 1 will be accessed data which is contiguous in memory. So you want the loop of I to be the inner loop. Not this. So don't do this. Memory are not coalesced. Do this. Okay. Any questions? Okay. Then let's move to some general topics. So we've talked about latency. So latency might just be the amount of time it takes the first time you access some memory, but also means the time it takes to essentially tell the GPU to schedule on the GPU all those waveforms. So all those tasks you define in OpenMP, at runtime needs to somehow be sent to the GPU. So what the compiler does, it prepares a computational kernel and essentially sends it to the GPU. But that takes time. Okay. It's a time you pay. It's only at the beginning, so it takes a while for the kernel to get started. But once everything is on the device, everything then can run. So typical time for issuing a kernel of a device on a MI210 will be, it will depend on how many arguments, how many things you're sending to a GPU, but expect to be something like 5-10 microseconds. So that means if you the region you are offloading to a GPU has very little work on it, and it's really, really fast, and it takes more, and it doesn't take much longer than 5-10 microseconds, that means your performance will probably be limited by kernel latency. So you might have a situation where you launch a lot of very small kernels, and all your time is spent in issuing or sending the instructions to the GPU. So how can you avoid this? The easiest way is to just have bigger kernels. So try to avoid having kernels that are too big. Again, this is the same on the same stream of making sure that there's enough parallelism if you want, but also that there's enough instructions happening inside the threads in order to hide the latency. So merging small kernels together often helps. We've talked about data movements. Now, data movement is slow. Moving data between CPU and GPU can be really, really slow. It's like orders of magnitude slower than moving data around inside the GPU. So try to do it as little as possible. Good ways to try to enter data and exit data, so that all the data is mapped once at the beginning and then taken over once at the end when you actually need the results. If you're using temporaries, then try to allocate memory directly on the device, as you can allocate you can allocate memory directly on the device using OpenMP. You might want to use the alloc clause to not in excess. If you use a map directive, it will transfer data from the CPU to the GPU. You might not always want to do that if it's just some temporary data on the GPU. So you might use the alloc directive. If you do need some data to be synchronized at some point, use the update directory. And you might want to consider using also first private clause. It should be the default for scalar data, but it might make sense also for other types of small amount of data. If someone has already written something really fast for you, do use it. So try to use libraries as much as you can. It probably does not make sense to write your own Poisson solver. There are other libraries that have Poisson solver already made implemented. No need to write your own FFT. There's already libraries that can do that. So some libraries are vendor independent, so they will work on any GPUs. For instance, Magma. However, some others will be vendor dependent. For instance, you might want to use RockBlast or QBlast. So you might have some code that essentially can switch between vendor-specific libraries. And the way you can, with Sino, you can interface with libraries with OpenMP by using isDefined pointer and asDevice address clause. Use asynchronicity if you can. So this could, there are different cases where it might be useful. You might be doing most of your computation on the GPU, but if you have stuff happening on the CPU, try to overlap it. So you can use this using asynchronous task. So essentially adding the no-wait clause and then making sure to synchronize the CPU and the GPU using task wait. It can also be useful when you have a lot of very small core kernels, which are difficult to merge together in bigger ones. So it can be useful to use no-wait so that you can offload multiple kernels at the same time on the GPU. It's also a way to additionally hide the latency. So the time it takes to send your computational kernel to a GPU. All OpenMP pragmas and directives do have an override. So the more compact, the less you have, the better. For instance, take this C++ case, where you have a PragmaMP target teams distribute, then you have some code inside, and then inside you have a separate directive for PragmaMP parallel 4. You can do this, and sometimes you want to do this. So for instance, this is useful if you want to share. In other cases, often what you want really is that all of these two statements are compressed together in one. So instead, use PragmaMP target teams distribute parallel 4 if you can. This will, compilers can usually do much more efficient code if they're all collapsed together instead of separated. And this is the same example, but with Fortran syntax. Okay, so in conclusion, make sure there's enough parallelism to fill all your compute units. Avoid as much as possible branches. So don't have your threads all do the same thing. Try to avoid them doing completely different things and calling different functions. Try to optimize the way access is, or the way you access the memory. So if you have two loops, if you have nested loops, make sure try to have a collapse statement, so collapse the two loops, and then make sure the inner loops is accessing contiguous elements in memory. And make sure there's enough work on a kernel to hide the latency. It takes a while to submit work to the kernel. But make sure it's not too big, otherwise you run out of registers. Any question?
I've got one thing I'd like to say. You just reminded me when you were talking about offloading more than one kernel to a GPU, and I made a mistake in the presentation I gave, and that was the scenarios whereby multiple kernels that have been offloaded to GPU, whether or not they would run serially or in parallel. And I was talking about it depends on how many compute units there are. And I was then talking about the number of iterations in the loop that you're offloading. How does that compare to the number of compute units? What I meant to say, it's how does it compare the number of iterations in the loop to the total number of cores on the GPU. So that's the number of compute units multiplied by the number of cores per compute unit. That was, yeah, I'll see if a note or pop-up text can't be added to the slide in the recording. That's all I wanted to say, Luca.
Okay. It's actually a very good. So essentially, you can think of each compute unit can execute one instructions at a time per web front per cycle. So all operations are executed in cycles. So at each cycle, you essentially can do one instruction at a time per compute unit per web front. So that is correct. Only the you want more than you want to have several web fronts scheduled at the same time, because typically those web fronts will get stalled for a very long time. So while you can only execute simplified way, you can only execute one web front per clock cycle. You actually want, well, ideally you want all 32 on them, so that you can hide latency. So if one stalls, you can just switch very quickly to the other ones on AMD 210.
So I can see that there appears to be no questions in the chat, and there's nothing on the Etherpad.
Regarding, so there was a question before about some directives do not work on Fortran, so I've tested that. And it is true that some, like get thread max, do not seem to work with Fortran. My guess is that they're just not implementing the compiler. So if you had a chance of playing around with OpenMP 210, you'll find that our compiler is old, needs an update, and it's quite buggy. So there are many things like that, especially the Fortran one. So yeah, I've been able to get, yeah, I got the same error when I tried. I will say with this recurrent thing, which is Fortran implementations with OpenMP tends to be less reliable than the one in C. Vendors usually implement things first in C, and it usually takes longer for them to get it to a Fortran compiler. So we have an exercise for that you can play around until the next time we meet. So we'll go through that, and this is a more complicated exercise where you implement a Poisson solver. So you can find it on the GitHub material. So in exercises, look for the Poisson exercise, and there are instructions on what to do, and we'll go through this next time. Essentially, it's about offloading. We give you a code that solves the Poisson equation, which is fairly common in science, for instance, in electromagnetics, or in computational fluid dynamics, to solve for vorticity. If you don't know what vorticity is, essentially tells you how fluid rotates. You'll typically use a library. Okay, you won't write it yourself. But in these exercises, I give you a Poisson solver, wait and see, and I ask you essentially to offload it to G++, to offload it to the GPU. It's fairly involved. So if you don't get to do everything, that's completely fine. And we'll go over the exercises next at the next iteration of the series. Does anyone have any question about the exercises, or? Okay, perfect. Then in the case, we'll adjourn in 2 days, still at 10. So see you there.
So what's the next session? Is it OpenACC at the same time, and then you have the tutorials?
So yes, we'll go over the Poisson exercise essentially.
Yeah.
So kind of leaf coding, and then we'll talk about OpenACC.
Okay.
Yeah. We're talking very little about OpenACC. We're mostly telling you how you can do with OpenACC the same thing you can do with OpenMP. So we'll be telling you how the things map together.
Okay. Thanks, Luca, then. Bye. See you around.